Hello, everyone. My name is Sid Raskar. I'm assistant computer scientist here at data science team at ALCF. So today I'll be talking about how can you enable inference using a framework called vLLM on Aurora. Um, so before we get started with that, like I don't have slides, but similar to some of the earlier talks, I have detailed instructions on how you can enable this on Aurora. So these instructions are present on the same GitHub link under the Insight Hackathon branch. So in there, if you go to AI frameworks and vLLM, then you'll find everything that I'm going through today. Uh, so today in earlier talks, we learned about how you can like pre-train your model or fine-tune your model. You can evaluate it through PyTorch and other frameworks. So assuming you have your custom model trained and everything, and you have its model weights available to you, the next step, the next logical step is to use it for inference, and that's where most of the compute is spent. Now you can do this through like the basic Hugging Face transformers pipelines, but there are a lot of optimizations due to the specific kind of a workload that inference is, the challenges that it possesses, and hence there are like in recent years, there are some frameworks like vLLM or SGLang or Deep Speed Chat that have come out, and they give you much better performance. And by performance, I mean here like throughput, which we count in terms of how many tokens this particular like for a particular model, how many tokens you can consume or how many tokens you can output in a given second, and how fast you can do it, like the latency. So that's why we use these frameworks to make sure that you're utilizing your underlying hardware effectively and getting as much throughput as possible for your models. So vLLM is one such a framework that's been enabled on Aurora. So one of the novelty or one of the innovation that vLLM supports, it's called as this paged attention algorithm. So we wouldn't get into the specific details of this, but at high level, one of the most challenging part of LLM inference workload is managing this KV cache. And as your output size increases, this KV cache memory keeps on increasing. And the throughput basically depends on how effectively you can manage this memory. And paged attention algorithm basically takes inspirations from paged memory mechanisms from the operating system side and tries to implement that for the KV caches. So you can take better advantage of the underlying hardware depending on the GPU block sizes, etc. Uh, so yeah, like you can go ahead and read the paged attention vLLM paper for additional details. But today we'll be more focusing on how you can install vLLM on Aurora, and then uh, how you can use it for your models. So first things first, as you know, like the base thing that most of the AI frameworks that start here, like that are available, are through these model load frameworks. So these steps you have to do on your compute node to begin. So first, like maybe in interactive mode, you can get a compute node uh, through the instructions that are available on the Aurora documentations page, or like how you know through the previous talks. Once you have your compute node, you basically load this module load frameworks. Now, we'll not be using any of the PyTorch or other frameworks that are available through. So mostly uh, these instructions use this frameworks module for the Conda. But if you have Conda already installed in your local directory or somewhere else, feel free to use that Conda, and then you can ignore this first step. So basically, we will be creating a new Conda environment from scratch with Python 3.10 in this case, because the version of vLLM that's been tested on Aurora is vLLM 0.6.6 post 2, and that one requires Python 3.10. Then the next steps are to unload and use some of the modules for one API that are compatible with this particular Python version and with this vLLM version. Then at this location, Flare Dataset Software's vLLM install, I have provided some of the pre-built wheels for like dependencies of vLLM, like PyTorch 2.5 and PyTorch Vision and audio and like all other things. So just simply pip install them on your compute node. And once that is done, again, I have compiled vLLM from source and I have made the wheel available for you. So you can just install that vLLM 0.6.6 and that's basically it. This should take less than 5 minutes. And with these steps, you're good to use vLLM on Aurora compute node. Uh, yeah, so feel free to interrupt me through this talk if you have any questions. If not, I can move on to the next section. So
Are those instructions up to date with the latest frameworks module that was installed last week?
So these instructions should work with the latest frameworks modules, because I mentioned earlier, we are not relying on the PyTorch or other dependencies of vLLM that come from the frameworks module. So we are only using frameworks module for Conda. So you literally can skip the first step of module load frameworks and just start from Conda if you have Conda available.
Okay. All right.
So
Sid, would you mind if I jump in a little bit here?
Yeah, sure.
So Brian, I think I understand what you are asking. So so the current policy we have in place is we would like to have frameworks module N and N-1 both available for users in the system. And we would like to practice that going forward. So these particular modules that Seed is loading is coming from the N-1. So I understand your question, and we would like to revisit these and see if we can reach to the same level that Seed is willing to go with the latest SPAC unified module that we have here because it has new MPitch and all that. So does that clarify what you were going for?
Yeah, because it's like line 1 would load the new framework, but line 5 would unload the compiler that's part of the N-1 pack framework, not the N framework. Okay, yeah, that's fine. Okay,
exactly. So if you like look at this, like if we dig in a little bit deeper. Sorry if it is becoming a little bit technical, but let's. So the line 1, 2, 3, 4. Line 4 will try to unload the N-1. And then line 5, 6, 7 would bring back in one API release, which is 2025.0.5. It's just we will be using some of the MPitch modules for underlying communication, which are a little bit older. But the compiler pack will be the latest. The one API toolkit will be the 25.0.5, which is definitely not the latest, but that is the default on the current computing age. Does that make sense, Brian?
Yes, this totally makes sense. Thank you for clarifying.
Yes. Yeah, of course. Sorry, Sid, for the interruption.
Yeah, and I mean, thanks for commenting on that. I mean, I'm also working with Khalid on like creating like making this part of a frameworks module itself, so that users won't have to go through all these extra efforts. So they can just do module load frameworks in the future and just start using vLLM, just like they can start using PyTorch today. But that's working under progress. Okay, so once you have installed vLLM and it's available, so the next thing is accessing the model weights. So this is kind of optional, but you know, like to run any kind of inference workload, you have already trained your model, and those model weights are already available, and you can download those model weights from Hugging Face. And these weights vary from like few gigabytes, like tens of gigabytes for like 7 billion models, up to hundreds of gigabytes. And each user is going to re-download it. So to make it convenient for users, what we have done is like we have this common like directory address, and on here we have downloaded the most commonly used open source models, like the one from Llama or Qwen or DeepSeek, etc. So this doesn't have all the models, but the models that we have tested, so those model weights are already available there. So if you're also trying to work with the similar models, you can use these already downloaded models for your workflow. And in order to use these already downloaded models, all you have to do is you have to point your Hugging Face home and datasets cache directory to this particular location. Now, if you don't have, you're trying to, some new model comes up and you want to use that and it's not available at this location, then you can obviously set these two paths to some other location in your project directory, and you can download those model weights there. Or if you have some custom model weights, you can always do that. But all you have to do is change these two things. Or one of the common issues that I've seen is like many people try to download the models and write them to this location. So you only have read access to this location and not the write access. So if you're again trying to work with a model which is not present here, just change these two lines and you should be able to work with any of the model you have. The third line here is your Hugging Face token, authentication token. So though the model weights are open source, often all these Meta and other companies require you to request the model weights, and then they give you access, and then you have to get your Hugging Face token from Hugging Face website, and the instructions can be found here. And then you just replace this here. And all of this can go in your bash profile or in your submission script. The next two lines here are for Ray. So on top of for communication between the different workers, vLLM uses a communication library called as Ray, and we found that we have to set this Ray temp directory to these particular locations in order for it to work. Otherwise, we found that you could face some hangs on Aurora. So these are some of the common configuration steps that you have to do in order to get vLLM working on Aurora. Okay, any questions on this particular section? Okay, if not, we can move forward. So we know that each node of Aurora has 6 GPUs, and each GPU has 2 tiles, and each tile has about 64 gigabytes of memory. So this is the memory that will be used for loading our model weights, and as well as for KV cache that we'll be using during the LLM inference workload. So we found that in our experiments that so in vLLM, how do you parallelize your model? So there are various techniques like tensor parallelism and pipeline parallelism and expert parallelism. But for instance, if we just take an example of tensor parallelism, and you have 12 tiles in your on your node. So the way to achieve parallelism here, in order to use multiple tiles or GPUs, what you have to do is you have to set your tensor parallelism equal to whatever number of tiles you want to use on a given node. And then we found that like with TP1, you're only using one tile, and that is typically enough to fit a model with 7 billion parameters. For example, Llama 2 or Llama 3, 3.18 billion parameters. So 7 to 8 billion parameter models you should be able to fit on a single tile with tensor parallelism equal to 1. Now, another thing, like we know about this environment variable. So basically this is recommended that you set it to flat in order to expose all those 12 tiles. And we are recommending to do this because we also played with the composite, but we found that the rate doesn't map exactly nicely on like 6 GPUs. There is some discrepancy that arises. So we basically decided to keep this number of GPUs equal to number of tiles for this. So to use vLLM, this is what is recommended. And we also found that the performance, like when using the flat device hierarchy equal to flat, is better compared to composite for a model that fits into the single tile. And there are reasons, and we can get into that conversation, but this is what is recommended. to get the most performance out of a model that can fit on a 64 gigabytes of memory. Then this step is important to set up array clusters. So in order to, so I'll get into more details of this, but for now you can just assume that you're trying to use a correct IP address to set up array cluster. And this command is what will allow you to do that. So you should be running this on your compute node to get its vLLM host IP. And when you set up this environment variable, like that IP address is, so that vLLM also knows that array cluster is also running, and so that it doesn't try to set up that again. And we'll go into this again when into this later section when using multiple tiles. But for now, like, this is how you get the vLLM host IP. And then this next command is basically to start your array cluster. So basically, this is what you run on your array head node, and it's quite simple. Array logging level debug. So this is optional, but you just start the head node. Again, the verbose is optional, but just for your information. And then you set the node IP address equal to this IP address that you capture here with this default port. And we also found that another important thing is this number of CPUs has to be set to some higher number. We found 64 works good, but if you set it to like 1 or 2, then the process may hang or you may have some issues. And then the number of GPUs is equal to the number of tiles on your device. So there are 12 tiles on each node. So the maximum you should set this is 12. But in practice, we never use 12 tiles. We only use maximum of 8 tiles for pure tensor parallel execution. And maybe I can get into that right now. So the reason for that is like most of the open source models, so like Llama 2 or others. So in order to enable tensor parallelism, that number has to be divisible by the number of attention heads in that model. So particularly these models have like 32 or 64 attention heads, and that number is divisible by 8 and not by 12. And hence, even if we have 12 tiles in our node, we can only use 8 of them. If you set it to 12, vLLM will throw error because the underlying models are not designed to take advantage of 12 tiles or 12 workers. So yeah, these are the common configuration recommendations that you have to do to run any model. So any questions so far discussion? Okay, so if not, then I can move on to some simple examples. So we'll start with the simplest example, like to serve a small model. And by small model, I mean a model of size 7 or 8 billion, or anything that can fit on the 64 gigabytes of a memory on a single tile. So to run to serve a model, like this is the command that you have to use, like vLLM serve followed by the model name and the port on which you will be serving it, the underlying device that you want to use, and the data type that you want to use. So to serve a model on a single tile, you don't need to do anything else. Just this one command should work. And what I mean by that is you don't have to set up a array cluster because there is no communication. So you're just using one tile, and if your model fits into one tile, then this command is good. It's more than enough. So this could be like your simple hello world test that, hey, like my model is working and it's been served. And then if you want to use the multiple tiles, and if you have like a bigger model, let's say like a 70 billion model, like Llama 3.3 70 billion model, then you can use multiple tiles. But in order to do that, you can't just do vLLM serve. You have to first set up a array cluster with a head node. And then once that head array cluster with specific number of GPUs is set, like 8 in this case, then you can do your vLLM serve, which basically, because we have already set up this vLLM host IP, it goes and understand that array cluster is already running and it connects to it, and then it serves the model. Now, these two steps are not there on like NVIDIA based systems or AMD based systems, because if Ray is not available, they fall back to Python's multiprocessing to enable this tensor parallelism distributed workflow. But on Aurora, it is mandatory to set up this Ray cluster for a distributed vLLM serving. So that's something to note. That's different. So far we discussed like how to serve models with vLLM serve using single tile or multiple tiles on the same node. So any questions in this part? Okay. So if not, then we can move to the next section. So similar to like in this case, we served, even though this model can fit on a single tile, we were using 8 tiles to serve this model. But more ideal case there would be to serve medium models, which are like 70 to 70 billion parameters. And this example basically tells it's exactly the same instructions, but instead of 7B model, we are using 70B model to enable this. But again, 70B model also fits onto the 8 tiles here. So this should work. So there is no difference when using like when between this and this, is just the bigger size of the model. The next complication or comes when you're trying to serve like a huge models. For example, the latest DeepSeek V3 with 652 billion parameters, or the dense model like Llama 3.1 405 billion parameter. In this case, you simply cannot fit it onto the single node, and you have to use multiple nodes. And in order to enable that, the steps at high level are same. Like first step is to set up your Ray cluster that we are setting up here as well. And the second step is to serve the model. But the first step of setting up the Ray cluster becomes a little bit more complicated here, because first you have to set up a Ray head node, and then you have to see what all what all other nodes are there in your cluster, and then set up Ray worker processes there, and then you have to tell vLLM that, hey, I have set up my Ray cluster, and then go serve the model. Now, in order to serve a big model like this, you can obviously use tensor parallelism method. So instead of TP is equal to 8, you can, for example, give tensor parallelism equal to 16. But due to the nature of LLM inference workload, especially into the decode phase, this becomes very communication intensive, and hence it's not recommended to use tensor parallelism when you're using nodes more than one. So the standard practice to optimize the communication is to use tensor parallelism within a node and pipeline parallelism across the nodes, so that if a model has like 32 layers, like in this case, we'll be running 16 layers out of that on node 1. Within that node, we'll be using tensor parallelism. And then all the activations from after layer 16 to 17 will be sent through communication channels to the next node. And again, there you'll have a tensor parallelism between the 8 tiles. And this will happen for each iteration, each token generation. So the general practice is to use tensor parallelism is equal to 8 for within a node, and you set the pipeline parallelism size is equal to number of nodes in your cluster. So if you're trying to serve this model using 4 nodes, then you should say PP is equal to 4 or 8 or 12 or whatever, based on how big your model is and how you want to scale it. So we have written this script to set up a Ray cluster. So I will get into the details of this script, but for now, the workflow is basically from your, assuming you have an interactive job with 2 nodes, then you basically source this script from your first node, and it will automatically go and see that you have requested 2 nodes, and then it will set up a Ray cluster on 2 nodes. And then you call the main function in this script, which will do certain processes on the head nodes, certain on the worker nodes. And then you simply serve the whatever big model that you have. Now this instruction is pretty much stays the same, like vLLM serve the name of the model, the port, tensor parallel size, pipeline parallel size is equal to number of nodes that you have. The one new argument that you see here, which you can again use for all other models as well, is this max model length. Now, this is basically used uh, to limit how much should be the maximum tokens that model can handle. So that's basically number of input tokens plus number of output tokens that your model can handle. In this case, we have set it to very small value of 1024. And this is basically used by vLLM to allocate the KV cache before the model execution. So if you have and if you don't set it, then by default it uses whatever the default max model length of your model, which in case of Llama 3.1 models is around 128K. But if you don't use this here, that will basically means it's trying to use 1028 and it will try to allocate that much memory. And in case of the huge model like this, you cannot fit it in 2 nodes. So you'll probably have to use like we had to use like 8 nodes in order to fit that big of a model. So you can fit it in lesser number of nodes by reducing the max model length of your model. So that's why I have used this particular parameter here in order to fit this big model's KV cache onto the 2 nodes. Okay, so next I plan to get into the details of this setup ray cluster script. But before I go there, any questions with this workflow or the parallelization strategies, etc.? Okay. Okay, so next we'll go into the details of this setup ray cluster.sh script, which again I have provided here onto the same GitHub repository. So we'll start with the main function here, which is at the bottom here. So basically what we are doing here is we are going to read from PBS node file how many nodes we have. We are going to get them into number of nodes. We are going to print that. And yes, like this has to be used for distributed inference serving. So we are just making sure that there are at least 2 nodes there. Then we are going to assign the first node in the list as a head node and everyone else as the worker nodes. And then we are going to call these functions which are in the same script, which are like setup environment. We are going to make sure that no existing ray processes are working. And then we are going to start a ray head. So let's see what this setup environment does. So everything that I have mentioned, like the common practices, so they are all here. So first I set up the proxy for ALCF. Then here, this part is what you have to change. So here you have to give wherever you put this setup ray cluster.sh script. So you just have to change this path to that script, which is common setup script. Then you're going to load your frameworks module. You're going to activate your vLLM environment, do all these other module uses and unloads and adds. And then these are some environment variables recommended for the performance. You're going to set up your Hugging Face token, your Hugging Face home directories, your ray temp directories, etc. And then you're going to get this HSN IP address, which is also going to be your vLLM host IP address. And that's basically your setup, like the initial setup that will happen on each head as well as the worker node. Then you're going to, the other function there was to stop ray. So we are just going to make sure that no existing ray process is working. And then you're going to run this ray start ray head node, which is same instruction as we used for a single node inference earlier. So it's basically the same instruction, but basically what we are going to make sure here is like we only run this on the head node and not on the worker nodes. So that's what those 3 functions in the beginning do, which are these, like you set up your environment and make sure your ray head node has started correctly. Now, once your ray head node has started correctly, you're going to SSH to each of the worker in your workers list, and there you're going to basically set up these environment variable, like export your Rayhead IP and the common script, which is the same script, and you're going to set up the environment there, stop any existing Ray cluster there, and going to start Ray worker there instead of the head node. And Ray worker node is nothing but this script here, which basically is another Ray command where you say Ray start, like I have 8 GPUs, and the head IP for the Ray head is this, and start the Ray worker here. And that's it. With that, you should be able to have a Ray cluster setup done with a head node and multiple worker nodes, whatever you have in your PBS node file. So that's that. So any questions with the setup Ray cluster file or script? Any questions? So so far what we have done is like we are serving our models, various models, and we saw how to set up environments to do that and serve them. But what's next? How do you exactly use these models? So for that, I have provided a couple of examples. So one of the example is for the online inference. So when you're doing this vLLM serve, you have your model served there as a server. So you basically connect to that, and then you ask your questions to that, and you get your replies. So for that, I have provided a very simple test example for OpenAI example based on OpenAI's API, which is again here. So in this example, like it's very simple. We don't need any API key here. We are just going to connect to the server that we just created using vLLM. So it's on localhost on that particular port number. And in here, this is a typical OpenAI API, right? So I'm asking this question here. Like I'm giving this command, and yeah, I'm asking it question like tell me a joke, and it will respond with a chat. So once you have this vLLM serve for whatever model using a single node or multiple nodes, if you run the script, it will connect to that server, and you can start talking to this, and you can build more complicated workflows and agents and whatnot on top of this once you have the model served. So this is a simple like hello world example for using OpenAI API. Similarly, I have also given this offline inference example. Now for this, you don't have in order to do offline inference, you obviously don't have to do online vLLM serve. So like you don't have to serve the model. When you run this script, it will automatically like serve the model and also benchmark it. So for that, I have given this again offline benchmarking script, which is again a very simple script. Here you can give different model names here. You can select the number of input tokens, output tokens, batch size, what tensor parallelism size you want, what maximum model length you want, and it will automatically generate some random input text for you. For example, here it's just going to generate France, and you're going to get some garbage output. But the main idea here is to make sure that offline inference is working and measure the performance, the benchmarking script. And here, basically, you're going to create this LLM class, like you're going to initiate this LLM class to run on XPU device and give all these model parameters to it. And then you're basically calling it with that random input, and you're basically measuring the start time and end time here with those prompts, random prompts, and that should give you like idea about what is how much tokens it's producing, what's the throughput, what's the latency, etc. So those are some of the example scripts that you can try to get started with vLLM. Okay, so that's all I had to present. And if you have any questions,